I hope you enjoyed the evening out yesterday and are back here full of energy to start the day with 2 workshops. And I would like to welcome Olga as chair of the workshops for a short introduction.
Thank you, Leonie. Dear participants, it's my pleasure to start this morning with our workshops. They're very different, but both are interesting, so I would like to attend both of them. The first one will be here. It will be on machine learning and artificial intelligence with moderator Haik Shokaran. He's there. Yeah, he's just speaking. And so any things that you would like to know about techniques and methods of artificial intelligence in cooling of HPC devices on digital heritage, and the said speaker will speak about security system. Please come here, and any possibilities for future cooperation you are interested in will be discussed here. And the second workshop will be on satellite-based research, geoscience, with Chris Atherton. You have seen him yesterday with very interesting talk, so please follow him. From starting to turn to the right, then straight, before coffee indicators, you go to the right, yeah, and then to the first floor. It will be in another building, so who would like to know more and explore that opportunity of collaboration and new ideas in geoscience, please follow the second workshop. It's about all from me. Both are interesting and both are very important. So just select what would you like to. And then we'll come back at 12, yeah?
One went up, okay. Now it works. You can lower, thank you. Should be fine, okay. I'll try to. Better now? Okay. So, do we want to get started? Or should I wait? Do we want to give 15 minutes additional? Should I wait?
No, you can start.
Interesting. Yes. Okay, ladies and gentlemen, let's get started. Good morning, everybody. So everyone who has signed up for AI workshop is this place. Everybody who wants to attend the second workshop, so Chris just left, so please follow him. So my name is Haik Shakurian. I'm representing Leibniz Supercomputing Center in Germany, Munich, and I have pleasure to actually act as a moderator for today's workshop on AI technology. So we've got rather interesting agenda today, if my pointer just works. So excuse me, my pointer doesn't work. So it seems Battery? Back to school. Nope. Now it works. Perfect. So sorry for this. So we've got a rather interesting agenda for today. We'll discuss 3 different topics of AI covering 3 different disciplines. So we'll talk about how machine learning helps us to tackle problems in modern HPC data centers. Then we'll talk about how actually AI helps us to do natural language processing and tackle aspects of cultural heritage. Then we'll talk about how actually machine learning techniques help us to solve security issues. So, and at the end, we plan to have a small panel discussion where we will try to elaborate the possibilities of having further collaboration with EAP countries. So, but before we deep dive into the specifics of all these machine learning applications, I would like to actually open my talk by giving a short introductory, especially for the folks who are outside of the computer science domain and AI in general. What is AI and why are you actually sitting today here, and why do we want to have this workshop on AI today within the scope of this conference? So, first of all, I'll try to give a broad definition of artificial intelligence. So, AI is a broad field that focuses on the usage of computers that help us to solve problems requiring human-level intelligence. So it is strongly believed that as electricity transformed our life, the way we lived 100 years ago, AI is going to have a similar impact. And in fact, we already see, right? So AI has its applications in the web search. So when we do today web search, AI is helping us out. When we do these Alexa devices that we have at home, Alexa, Siri, everything is already on AI. Even if we go to a bank and ask for a loan from the bank, some of the banks already use AI to determine if you are actually eligible to get the requested loan, right? Or even if I go in Munich to get a car at Sixt company, for instance, they give me a person-related rate for the specific car based on the history of how I drove, right? So just to be sure that we are all on the same page regarding terminology, so AI is, as mentioned earlier, basically covers the class of algorithms that aim to mimic the human intelligence. So machine learning now is a subset of artificial intelligence that uses statistical techniques that rely on vast amount of data to actually build your model, and this model will help you to do certain decisions. And what is cool about the machine learning is that when you get this model, then this model automatically adjusts to the changes that happen without being explicitly programmed for that. So deep learning is yet another subset of artificial intelligence and machine learning that relies on the notion of artificial neural networks that use large data set to build you the model. So as you can see from this graph, AI was around starting from 50s. The problem back then was that the supporting hardware infrastructure and the software was not ready to allow us to completely evaluate the potential of AI technologies. So nowadays, thanks to the breakthroughs in hardware and software, supercomputers today enable the full applications of AI, right? Because we have the required computational power, we have the required storage capacity. And to illustrate this, you can already see that AI is almost everywhere. It's in media and entertainment, helping us to do natural language processing or language translation. So in Facebook, when your international friend will post a status, there is a small button which says translate. Each time you click on that translate, in the background, you have a recurrent neural network working for you. So we already see that AI is coming into healthcare. We have AI already helping us to tackle problems of personalized treatment. It helps us to diagnose if a person has a cancer or not, in some cases even better than a human professional. And it helps us with problems of autonomous driving. It also helps us with security. And I've got a great pleasure to announce that we are going to talk today of one of these aspects of the security and how is AI going to help us there. So, but before we proceed any further, in my conclusion of the opening talk, I want to actually open the floor for further discussion within this audience afterwards, after this workshop. And as a person coming from the HPC field, I couldn't resist and not to talk about the interesting topic of convergence of artificial intelligence and high-performance computing. So if you think about artificial intelligence, then in my personal opinion, it has a lot to learn from high-performance computing community, from HPC community. Why? Because HPC actually has been, for decades, been dealing with the problems of deployment of large parallel applications onto big systems. And not only that, the HPC community was tackling the problems of how we can actually make that deployment the most efficient. And artificial intelligence, in that sense, is a typical high-performance application because it requires a vast amount of computational power. But the interesting thing is that in contrast to typical traditional HPC applications, AI requires also a large amount of data. So in some sense, it's bringing new direction. So as a computer scientist, for me specifically, what is more interesting is that for decades, HPC was pushing for higher precisions, right? We were going from single precision to double precision. So what's happening on the AI side? So AI doesn't care about precision. Even more, they are happy to reduce this precision, and most of the AI applications are happy with half precision, so 16 bit, because you are doing approximation on fly, and you don't really care about the high precision. So the message I want you to take from this is that AI is already using HPC, and it is foreseen that this usage will increase with the time. But the question to answer here is, how is actually AI going to impact high-performance computing, and how HPC field is going to adapt to these changes? So feel free to share your lessons. So what you as an AI user are expecting from HPC, what they should do for your life as an AI engineer to make easier, and vice versa. If you are an HPC scientist, what do you actually want from this AI community to make your life easier, to understand them better? So with this, I want to conclude my opening talk, and if there are any questions regarding that, please feel free to ask regarding organizational matters or something like this. If not, we just proceed to the next talk. Are there any questions? Okay, if this is not the case, then I guess we are good in time and we can proceed to the next talk. Okay, so thanks again to Institute of Information and Automation Problems for having me here. It's a great pleasure and honor to present our recent R&D results to you guys. So, and also to partners of EAP Connect. So, as mentioned, I'm Haik Shakurian, representing Leibniz Supercomputing Center, one of the biggest supercomputing centers in Germany. And I will be talking today about a machine learning-based approach, how it helps us actually to do our warm water cooling efficiently. And I'm going to talk about what that warm water cooling actually means. So here is the agenda of my talk. So I will start off by giving you a high-level overview of our data center. Then I will basically give a brief description of our warm water cooling infrastructure. I will outline the energy efficiency challenges that modern data centers do face nowadays. I will talk about our machine learning-based approach that helps us to reduce the costs, operational costs. I will discuss the results, present some new results actually to you that are yet unpublished. And we'll talk about our future steps, and in conclusion, we'll happily ask you questions if there will be any. So here you see the outer view of our supercomputing center. So these buildings here are home to our offices. So this is basically where I sit, for instance. And this twin cube here on the lower left corner shows where we deploy our high-end IT systems. So this TwinCube has an IT equipment floor space of 3,160 square meters. Infrastructure floor space of 6,393 square meters. So it's a huge thing. So who are we as a data center? So first of all, we are a generic IT service provider to all Munich universities and to research institutions in greater Munich and Bavaria. So as one of the 6 hosting partners within the PRAISE consortium, we also provide a tier 0 HPC service to European researchers. So European researchers who are part of the PRAISE consortium can access our high-end systems. So here you see the world's first high-temperature direct liquid-cooled supercomputer called SuperMOOC. So, and as you can see, it consists of 2 installation phases. So first phase was deployed back in 2012. It is based on Intel Sandy Bridge processors and has a peak performance of 3.18 petaflops. So this means 3.18 times 10 to the power 15. So it's 3,000 times billion operations per second. So only this small part can do your operations that fast, right? And it has an energy efficiency rate of 0.85 gigaflops per watt. Under normal operational conditions, we consume around 2.3 megawatt. If we stress the machine under LIMPAC benchmark, which is used for creation of top 500 list, the fastest supercomputing, so the list indicating the fastest supercomputers in the world, then our power consumption rises to 3.4 megawatt. So we burn a lot of power. So back in 2012, when the SuperMOOC was deployed, it was the fastest supercomputer in Europe and 4th in the world. So in 2015, we went further and installed the second phase of this big machine. So what is interesting about this phase 2 is that it's based on newer generation of Intel processors, so it's Intel Haswell processor. And as you can see, we get almost the same performance, 3.57 petaflops, so 3,570 times billion floating point operations per second. And in that regard, our floor space is reduced, so it's 1/3 of the floor space that SuperMOOC phase 1 had, right? And by telling you that SuperMOOC is directly warm water cooled system, I mean that its active components, like processor and memory, are directly cooled by the water with up to 45 degrees C. Can you imagine that? 45 degrees C. And this number allows us to do a cooling, free cooling, so we don't use any refrigerators, any chillers to cool our water. So we pipe the water to the roof, we use the outside temperature all year round, as in winter, as in summer, and then pipe back that water into the system. And we can withstand with up to 45 degrees C inlet temperatures. So here you see actually our recently deployed SuperMOOC next generation system, which is our flagship system. So it has aggregated peak performance of 26.8 petaflops supercomputer. And currently we are the fastest supercomputer in European Union. And why European Union? Because Swiss guys just outperform us just for a little bit. And according to the top 500 ranking, June 2019, we are actually number 9 in the world. So SuperMOOC NG nodes are based on the next generation of Intel processors, so it's Intel Skylake processor. We use Intel's Interconnect OmniPath, which they actually now are not supporting anymore. So, and as compared to so we decided to continue the tradition of warm water cooling because it's really energy efficient. So it's much more energy efficient to remove the heat with water than with the air. And I think that's clear why. So, but with SuperMOOC NG, we went even further. So we increased the withstand. So with Lenovo and Intel together, we worked to design a node that will now withstand the inlet temperatures of up to 50 degrees C. So, and typically, depending on your workload that you will pipe on the servers, your outlet temperature can be as high as 60 degrees C. And usually what we do to be even more energy efficient, we pipe this outlet temperature to special devices called adsorption chillers to generate us cold water. And now your question will be, why the hell you need a cold water, right? And the cold water is used to actually cool down our network and storage equipment where you can't really use warm water cooling. That's just hardware specs that you can overcome. So I've got actually a small animation showing you how the water flows. So it enters here, goes through the processors. So again, this part is just one node. This part is the second node. Each node features 2 Intel Skylake processors. Here you see them. Then we have 6 DIMMs, so dual inline memory modules. And as you can see, water goes through these processors, through the memory blocks, and then also for the second node, and goes out. Okay? So regarding the storage stuff, so SuperMOOC features 50 petabyte capacity of storage of parallel file system, and we have I/O bandwidth of 500 gigabytes per second. So what is interesting about SuperMOOC NG as compared to the previous generation of the SuperMOOC systems is that we now have also a dedicated segment for cloud computing, right? And so SuperMOOC NG itself is a pure x86 machine. So we don't have any accelerators, any GPU cards attached to that. But on this cloud system, we actually have NVIDIA Volta 100 GPUs. And we have actually really huge RAMs there. And this is done to keep our machine learning community happy, because they need a lot of RAM and they need accelerators. So this much about SuperMOOC NG and our flagship system. So, and as you can see, hosting such kind of high-end infrastructure costs LRZ a lot. And here you see our energy costs from 2000 to 2018 and some estimates for 2019, 20, and 21. And as you can see, the energy costs kept rising. Now you can ask me, like, wait a second, why are your energy costs rising if every new generation of hardware is more energy efficient? Well, you will be totally correct there. The answer to your question would be that we increase the density and also system performance, right? Each time we want to buy a new system, to build a new system, we want it to be more performant than the previous one. And that's why this increase. What is also interesting is that this increase translates to high operational bills. So on annual basis, currently, we pay around 8 million euros. And this number, ladies and gentlemen, is just pure electricity costs. So no maintenance, no hardware, no staff costs, just electricity. And this rise in operational costs is also due to the fact that government is actually penalizing us for using power, right? We call it in Germany Energiewende, which is basically government has a policy to protect for the environmental protection, and we used to pay for kilowatt hour back in 2000 around 7 cents. Nowadays we pay more than double, around 70 cents. And this number is yet even low than the bill I pay at my Munich apartment. So I pay, for instance, around 30 cents per kilowatt at my home. So to make life even worse, now data centers are, as a large power consumers, affect the stability of the underlying power grid. And that's why when you as a data center will go and talk to your utility provider to get a power, they will actually bind you to certain power bands that you have to adhere. So both maximum and minimum. So usually we can't, due to that reason, we can't shut down completely our system because we would be penalized, even for one time. And this penalty can propagate to your entire yearly operational bill. And this penalty is really big, reaching billions. So just to give you an idea of that, so here you see the power profile of LRZ for a 5-day time frame back in January 2014. So this black curve here illustrates the complete power consumption of our data center for this 5-day time frame. The purple line here illustrates the power consumption of our flagship system, back then only SuperMOOC Phase 1. And this red curve here illustrates the power consumption coming from the cooling infrastructure. So this dotted curve here, the blue one, illustrates the power consumption for our smaller Linux cluster systems. This brown curve here illustrates the power losses that we have from PDUs or UPSs. And this area marked in green illustrates the wet bulb temperature. So what you can see is that our data center profile is affected as by the underlying flagship system, high-end IT system, so our supercomputer, but it's also affected by the power consumption of our cooling infrastructure. That's why if we want to stay within the indicated power bands that our utility provider will force us to, we have to actually have predictive mechanisms that will allow us to see whether we are violating any of these curves or not, right? So just here is 2017 data to cover the possible question that, hey, this is 2014, how does it look now? So it's the same, so we have the same impacts. So another interesting question is, that I usually get is about the renewable energy sources. So Germany is an active advocate of usage of renewable energies. And the obvious challenge with usage of renewable energy sources is the dynamic of the available power at a given point of time. So you here can see these bar charts, 2 bar charts, show you the power generations of solar and wind in Germany for the complete time frame of 2018. And as you can see, they are also fluctuating. And this leads to certain instabilities to the supporting power grid that lies in beneath. So now, data centers can actually help you out with this. Because as large power consumers, if you have a certain control mechanisms that will allow you to adjust the power in orders of several megawatts just in a short time frame, then it's actually a win-win situation because you can balance it out. To give you an example of this, consider a simple data center that uses 5 cooling towers to cool your IT equipment. So to say, to remove the heat that is constantly generated by your IT equipment in your data center. So let's assume that this curve shows you the power profile of your cooling infrastructure, and this curve shows you the water inlet temperature that you would pipe into your compute nodes. So obviously from the hardware specification, you have a limitation on the maximum inlet water temperature you will pipe into your compute nodes. And assume that you have also a certain power cap set by your utility provider, and this power cap is also propagated to your cooling infrastructure, right? So what comes now interesting is that assume that at time t, you have to take 2 of your cooling towers into maintenance. And the obvious question you will be asking yourself is, hey, can I continue running my supercomputer or not? Or should I completely shut it down because I won't manage to actually adhere these power bands? What is even more interesting is that assume you have a job in your job queue that has actually a big requirement of 470 compute resources. So it wants to utilize 470 compute servers. So the question you would be given is, can you actually run this job without affecting all these constraints or not? And this again motivates the fact that we really need predictive mechanisms that will allow us to evaluate what will happen in given scenarios. And that's why we do develop these predictive frameworks. So here you see the schematic overview of our cooling infrastructure, and I know this looks really complex. The good thing is I'm a computer scientist, not a mechanical engineer, and I'll try to make this easy. And the other good thing is that we are going to focus on really small part of this. So this part is only responsible for our warm water cooling infrastructure. And this part, as you can see, consists of 4 identical cooling loops indicated as KLT 11, 12, 13, 14. So how does this work? So the water is piped out from the compute systems through the distribution bar to the cooling loop, to the given cooling loop. Gets cooled there, gets piped back to these systems, right? So let us have just a zoomed in version of one of these cooling loops, say KLT 14, because they are all identical. So here, the water enters the cooling loop from the distribution bar here. So this is your distribution bar. So it enters via hydraulic gate. We put the hydraulic gate in order to solve the pressure issues. Then it gets pumped through the help of this redundant pump here to the heat exchanger, gets cooled, and is sent back to your IT system. So this is just a typical heat exchanger that you will have also in your car. on this part where we pipe the water into the cooling towers, we actually mix the water with glycol. And we do this in order to prevent the water from freezing during the winter times. And this water gets then to the cooling tower. We have sprinkler pipes that will sprinkle on the walls of the cooling tower. And we have also the fans that help us to do the cooling. And here are some real-world pictures from our roof just for you. So what are we trying to predict? We are trying to predict the cooling efficiency of our infrastructure. And LRZ, back in 2013, has developed a four-pillar framework that basically indicates the main energy and power consumption aspects. And we do believe that in order to be the most energy efficient, one would need to look at all these pillars in a holistic manner. So you have to, in order to understand what's happening in your data center, you have to consider what's happening in your building infrastructure. You have to understand what's happening on your system hardware part. You have to understand what's happening on your system software part. And you have to understand what type of applications you are running at a given point of time. So for that, we have developed a high-frequency data collection monitoring toolkit called PowerDam. And using this PowerDam, we have put analytical and adaptive models that actually help us to do energy-efficient resource management and scheduling. So what I'm going to cover today is the next step, basically, which tackles the Pillar 1 and Pillar 2, so building infrastructure and system hardware. And we do this in order to have a global optimization framework that will touch all these pillars and also interact with the neighboring buildings, with the utility provider and environment. So this is exactly what we are trying to predict, the coefficient of performance of our cooling infrastructure. So it's basically a fraction of the amount of the cold your cooling infrastructure will generate by the amount of power you will put in to generate that amount of cold, right? And as you can see, this is a unitless metric, and indicating the higher this number is, the better your cooling infrastructure is. So this is basically a common metric for evaluating the efficiency of your cooling infrastructure. So in our current setup, we can measure this metric in 5-minute intervals, and it's not a limitation of our software components, but it's limitation of our sensoric that we have on our building automation systems. So, and we do use a neural network approach for doing this prediction. So, but a specific type of a neural network. So for those who are not familiar with the notion of neural networks, here is just a simple sketch of it, where you would have, so a typical neural network consists of an input layer that takes the input. You have an output layer that for each input layer vector will generate you an output, and you have layers in between called hidden layers. So the more these layers are, the deeper your network is, and that's where the notion of deep learning comes. So in a typical setup, you have a training data set. So what you will do is, so this neural network which will take each instance of this input, and for each input will generate an output. So once generated an output, it will compare with the ground truth. If the generated output is correct, so it coincides with the ground truth, your training framework will increase the synaptic weights, so basically the weights of these connections between neurons that contributed to the generation of this correct answer. If the output was incorrect, then these weights will be penalized and reduced, the ones that contributed for that answer. So that's kind of simple, and I know I did it in a high level, but this is for those who are just not familiar with the notion of neural networks. So the problem, obvious, with the traditional neural network is that they don't have a persistence. So we as humans, when we start to learn something new, we base our new knowledge on the understanding that we had before. But the question is, how can we achieve this with neural networks? So for that reason, artificial intelligence community has came up with a notion of recurrent neural networks that basically includes certain loops that allow you the information to persist. So if you think about this, just a typical block referred to as NM block in your recurrent neural network, So it looks at some input IN and gives you an output of ON. And you have here a loop. So what happens if you unroll this loop? It will look like this. And this shows you that this type of architecture of recurrent neural networks are ideal when you deal with data of sequence type, right, of a list type. I'm not going to go into details because of the time here, but I want to tell you one thing, that these recurrent neural networks have already shown a successful application in a wide area of applications ranging from speech recognition, so each time you will put your Siri or Alexa, there is a recurrent neural network working for you, up to time series forecasting, you will do a stock market prediction. The other problem with the recurrent neural network is, okay, we said that it helps us with the information persistence, but how actually good are they in real world? And for that, let me bring in a short example that considers a language modeling and prediction problem. So let's take this simple sentence, Paris is the capital of, right? So here the good thing is that the recent information allows you to relatively easily predict what is going to happen as the next word. So now, what happens if your context is big? So you have to really consider a bigger sentence. And the sentence goes as follows. Paris is a major European city and a global center for art and culture. It is located in the northern central. So now, the recent information, only this part, allows you to predict that actually this part here should be a name of a region or a country. But in order to be capable of predicting exactly what is the region or what is the name of the country, you have to go back, right? And that's where recurrent neural networks suffer, actually. So recurrent neural networks are typically good when the gap between the relevant information and the place where you need to put the predicted word is small. So in practice, they usually fail when this gap becomes big. And the solution for that is long short-term memory networks invented by Sepp Hochreiter and Schmidt-Huber in 1997. And actually, this was a diploma work of Hochreiter, which was actually rejected when he submitted for a publication. But nowadays, even so, everybody, so all these speech recognition, Facebook translations rely on LSTM networks. And these are the networks that we also use at LRZ for predicting our different KPIs for energy and power consumption. So as said, we base our modeling approach on long short-term memory networks. We get our operational data from PowerDAM toolkit that was developed at LRZ. And just to be quick, I will show you the first results that we have. Here you see the efficiency prediction of our cooling infrastructure for the complete year of 2016, where we just trained the network on 2015 data. What is good about this, so we didn't do any fancy stuff with the data. We didn't sanitize it, we didn't do any gap filling. Just put the LSTM networks without playing with the data and see what it does. So, and since this is a real world data, you have also certain gaps, and these gaps can come from the thing that we had also maintenance in our building automation systems. What is good regarding this prediction, as you can see, apart that it follows quite accurately the trends, it actually was also capable of detecting anomalic behaviors. And this happened in November 2016, where my management thought that it's cold enough outside, and we are capable to reduce our inlet temperature from 39 to 30 and still cool the water just with 2 cooling towers. Unfortunately, that was not a correct decision, and our building automation system went crazy and activated an additional 3rd cooling tower unnecessarily. That's why your cooling efficiency dropped. But what was nice about this network was that it is actually capable of detecting those things. And I can now take this to my boss and say, hey, should we do this or shouldn't we do this? And this is actually helping you out with that. So now I'm actually going to show you new results, because you are friends here. We haven't yet published this, but for that reason I would ask not to put any videos or photos here, because this is unpublished data. So we went further and started to sanitize the data to increase the efficiency of our predictions, and as you can see, it helped a lot. So here is the prediction results for complete 2018, and also 2019 till August. So this year till August. And as you can see, we have rather accurate predictions again with CLP. So it's a bigger time frame that we looked at. And we also increased my mic. Hello? Yeah, okay. So we also increased the the list of supported KPIs, and the parameter is not working again. I have troubles with pointer again. And I think your part is hanging as well. It has troubles with loading the image. Anyhow, let me proceed. So we increased the list of supported KPIs, so we can now predict the power that is consumed by our cooling infrastructure. And not only that, we can predict the inlet temperature that you will pipe into your compute nodes. And what is even more interesting, while mathematically it might sound trivial, but your cooling infrastructure, just your cooling infrastructure operational data of your data center can help you with predicting the outside temperature. So in theory, and it works marvelously. So unfortunately, I can't show you the results now. But anyhow, so you can just use your cooling infrastructure data to forecast the outside temperature. Okay. So it has some troubles with loading the image. So what we plan to do in future, we plan to also extend. So first of all, we want to validate this also at other data centers. So I have to mention that I had the pleasure to work within a German project where we would try to analytically increase the forecasted list of our framework. Then I most probably need to get a student who will do a nice web interface for me that I can show to my bosses that this forecasted data can be easily accessible. And last but not least, we plan to deploy the solution into operations and hope that this solution won't explode our data center. So this is it. Unfortunately, my slides didn't work properly. I don't know what's happening. But stay connected. My name is Haik Shukurian, and if there are any questions, please feel free to ask. I'm happy to answer. Yes? Just, you are getting a mic.
Your opinion about difference between complicate automatic systems and intelligent systems. What do you propose? What it is difference?
Okay. So the question is difference